Welcome everybody to the online one-word seminar of the International Association of Mathematical Physics. We are very happy to have today Carolyn Zhang from Harvard University, who will speak about the anomaly-free symmetries with obstructions to gauging and onsiteability. Please go ahead.
Yeah, thank you so much for the invitation to speak in the seminar series. Um, this is going to be work with Wilbur Shirley, Wen Jieji, and Mike Levin. Hopefully, we will be posting it in a couple weeks. And I'll define what I mean by all these phrases shortly. Please do feel free to interrupt during the talk with any questions that you might have. Okay, so. It's a pretty broad audience, but in the condensed matter context, anomaly, the word anomaly is thrown around a lot. And it might seem like a complicated kind of topic, but it's actually familiar to a lot of condensed matter theorists. So, in condensed matter context, anomalies often appear at the boundaries of so-called symmetry-protected topological phases. For example, there's a 1 plus 1D cluster state that you might be familiar with, or topological insulators. There's a bosonic Z2 symmetry protected topological phase in 2 plus 1D called the Levin-Gu model. And these SPTs tend to look rather boring in the bulk. The symmetry is represented in a nice on-site way in the bulk, and it's a nice insulator in the bulk, but there's usually some non-trivial boundary physics. So for example, the boundary might host some degeneracy or spontaneous symmetry breaking. There may be gapless edge modes. If you have an SPT in 3 dimensions, you have a 2 plus 1D boundary, and there might even be topological order on the boundary. So what we usually find in the context of SPTs is that the bulk is rather boring, but the boundary, which hosts this so-called anomalous representation of the symmetry, has constraints so that it's actually rather non-trivial. An example is in this Z2 SPT that I mentioned in 2 plus 1D. If you look at the boundary, so you consider the SPT with open boundary conditions, what you find is that the representation of the Z2 symmetry on the boundary takes this non-trivial form. So this is an operator. R runs over the lattice sites in the 1 plus 1D boundary, and you can check that this guy squares to 1. And you can see that this is not an on-site symmetry, meaning it's not just a product of on-site terms, like a product of XR with R on every site. That's closely related to the property that this symmetry, you can't gauge the symmetry. You can't couple it to background gauge fields and let those gauge fields fluctuate. So to be more concrete, let's compare these two symmetries in 1 plus 1D. So we have two kinds of Z2 symmetries. One is this one on the left, which is just your usual kind of global spin flip symmetry. It clearly squares to the identity operator. These are just Pauli operators acting on these qubits in 1D. And on the right-hand side, you also have this operator. It's a finite depth circuit, and it also squares to 1. So it's kind of a Z2 symmetry. However, on the left-hand side, this is an anomaly-free Z2 symmetry. So what that means is we can write down a Hamiltonian that commutes with this symmetry, and this Hamiltonian has a unique symmetric gap ground state. The gap ground state is this all plus state, so it's the eigenstate of sigma x with eigenvalue plus 1 on every site, and it's symmetric. And this kind of system is kind of a standalone theory on its own, or the boundary of a trivial paramagnet. It's a non-anomalous on-site symmetry. However, on the right-hand side, no matter how hard you try, you would not be able to find a Hamiltonian that's symmetric and gapped with a unique non-degenerate ground state. So you can write down a Hamiltonian that's like sum over ZZ, like the Ising ferromagnet, but that's spontaneous symmetry breaking. And this guy on the left side, this sum over sigma x, definitely won't commute with this symmetry. So there's no kind of trivially gapped Hamiltonian. There's no short range entangled symmetric gap ground state. So this plus state, for example, is not an eigenstate of this symmetry operator. And this describes the boundary theory of a 2 plus 1D non-trivial Z2 SPT, which is described in detail in this paper. So you can see on the left side, the symmetry is on-site. On the right side, it's not on-site. And anomalies in this context have been used in many ways, and it's very useful because it allows you to constrain the physics. So it allows you to rule out certain phases of matter. For example, a symmetric gap, trivially gap phase of matter. I should mention that 't anomalies or anomalies of symmetries doesn't say that your theory is sick. Like in this case, you still have a tensor product Hilbert space. It's just the representation of the symmetry is so that it prevents you from realizing a trivially gapped symmetric phase, and it prevents you from gauging the symmetry. Um, okay, so there are, however, even though Tifft anomalies and have been studied for many years now, probably like 45 years-ish, uh, and they have been used to constrain physics in many non-trivial ways. The precise definition of a Tifft anomaly has still been debated. So in different communities, their understanding of Tifft anomaly may be different. There are two main ways that people view Tifft anomalies. There are other ways as well, but two of the main ways that people view Tifft anomaly is one as an obstruction to gauging the symmetry. And what we'll see is actually for the symmetries that we're going to be considering in this talk, which are finite unitary symmetries, this is the same as making the symmetry on site, which I will define shortly. Um, so one definition of a Tifft anomaly is that the representation of the symmetry prevents you from gauging it or making it on site. Another definition of a Tifft anomaly is an obstruction to a trivially gap symmetric phase. And we saw in the earlier example that both of those things happened at the same time. And the top kind of definition is maybe more popular in the high energy theory context, whereas the second definition might be more popular in the condensed matter context. Um, and there's actually been a lot of recent work. Even though the idea of Tifft anomaly came many, many years ago, there's been a lot of recent work trying to make these different definitions precise uh, on the lattice and for generalized symmetries. So not only like global zero form symmetries where the symmetry operator acts in all of space, but so-called higher form symmetries, non-invertible symmetries, all those things. So people are trying to understand Tifft anomalies in a general context and in a precise context. Um, Especially relevant for this work is that very recently, a couple months ago, Sahan Saif-Nashri and Wilbur Shirley showed that in 1 plus 1D, at least these two definitions are the same for finite unitary symmetries. So 1 plus 1D, uh, there's an obstruction to gauging a symmetry if and only if there's also an obstruction to a gapped symmetric phase. So these two are equivalent. And what we'll show in this work is that these two definitions are inequivalent in 2 plus 1D. So depending on which definition you take for anomaly, you might have a different evaluation of a symmetry. And when I say anomaly, I'll be referring to the second definition. So to make things more precise, I'm going to define what we mean by onsiteable. So when you are given a lattice model, so a bunch of qubits in some lattice structure, you can have a representation of a symmetry, UG, and we're going to consider finite unitary symmetry. So this is just a unitary operator acting on your Hilbert space. And we say that two representations of the symmetry are equivalent if you can get between them by tensoring in some trivial ancillas and doing a local unitary transformation. So this UGA are ancillas with an on-site representation of the symmetry. So they're trivial ancillas. You can think of them as in a product state. And they carry a trivial representation of the symmetry. This W is a locality preserving unitary. And when a locality preserving unitary has strict locality, so it takes strictly local operators to other strictly local operators, we call it a QCA, a quantum cellular automaton. Okay, so this is a rather natural definition of equivalence when you're talking about symmetries acting on a Hilbert space. You're allowed to tensor in some kind of trivial ancillas and then do a kind of a local unitary transformation or a local change of basis. And an onsiteable symmetry in this context is a symmetry that's equivalent to an on-site representation of the symmetry. So after tensoring in with some appropriate ancillas and doing this locality preserving unitary, your symmetry just becomes on-site representation of the symmetry. So it's just a tensor product of unitaries that act on each individual site. Okay, so another perspective on the result that we had is that if a symmetry is onsiteable, we know that there exists a trivially gapped symmetric state. Because if this is, for example, if this was just onsite, it's a product of onsite operators, then you can write down a product state that's symmetric under this symmetry. So this product state is just a state where each of these UGRs is equal to +1. So for example, if this was over a product over sigma x operators, then this is just the all plus state. So if a symmetry is onsiteable, there's definitely a trivially gapped symmetric state. However, you might ask the converse. So if there's a trivially gapped symmetric state, can the symmetry be made on-site? And a reframing of the previous, what I was trying to say previously was in 1 plus 1D that's true. In 2 plus 1D that's not necessarily true. Um, in this work, we will be considering lattice models in 2 plus 1D. And these lattice models have finite dimensional span on every site. And we allow tensoring with finite dimensional ancillas. And for simplicity, we're going to consider strict locality. So when I say like a locality preserving unitary, what we really mean are ones without tails. So they take strictly local operators to strictly local operators just for simplicity of the arguments. And the symmetries that we're going to consider are the most vanilla type of symmetry. So they're unitary, they're internal, they're finite, and they're zero form, meaning they act on all of space. And their charged operators are local operators. Um, and so what we're going to consider then are global symmetries, so a set of unitary operators acting on this Hilbert space. And symmetric Hamiltonians under the symmetry are just Hamiltonians that commute with the symmetry. And I know a lot of the more mathematically formal people will work with C-star algebras and all of that formalism, but in this talk, for simplicity, we're just going to take finite dimensional lattice and we can take the thermodynamic limit, and that seems to be sufficient for the arguments that we need to make. And I'm going to
Can I
specify,
ask you a quick question?
yes.
So maybe for example, do you call Hamiltonian itself as a generator of time translation symmetry or not? That's
So
not
if
usually that's not local, right? Is it
um,
localizable or not?
so e to the I h t is local, but it's not a finite symmetry, right? So because t can go from 0 to
Uh-huh.
infinity.
So it's
So here
uh-huh,
I'm going to consider like
finite
symmetry
group.
that's finite group symmetry, and
Uh-huh.
also like kind of one might want to generalize to continuous symmetries, but usually that's of the form of like a compact group where it's like say U1, where e to the I theta q, theta can run from 0 to 2 pi. So every element of the continuous group is still locality preserving. So for e to the I h t, then because t can be arbitrarily large, then that unitary operator in principle can take a local operator to an arbitrarily large operator.
Mhm. So
Um,
does that kind of statement applies to um so I want to distinguish two kind of conserved charges. Like when you have symmetry, usually you have kind of conserved charge, right? But some conserved charges
yeah.
are kind of strictly local, like U1 charge.
Mhm.
Some other ways, like sometimes, quasi-local or like even non-local, right? Some conserved quantities in general setting, accidental symmetry or something, conserved quantities. So they are non-local or they are not in this category because um, they are not necessarily like a finite group.
So they're not in this category. You might still say, what in general am I allowed to call a symmetry? And that is different in different communities.
Mm-hmm.
But what you might want, for example, is for every element of the group to be locality preserving. But then that would rule out kind of spatial symmetry. So it kind of really depends on what you want to get out of a symmetry, what you define as a symmetry. In this work, we're going to just work with finite group symmetries where
Mm-hmm.
every group element is locality preserving.
Mm-hmm. Okay, thanks. Yeah.
Yeah, thank you for the question. Um, yeah, but certainly one can ask what are generalizations to other kinds of symmetries. Okay, so again, the kinds of symmetries we'll consider are finite symmetries, invertible symmetries, unitary in lattice models in 2+1D. So an example of different kinds of symmetries, just to give you some intuition, is here. So as I mentioned before, in 1+1D, there's this onsite symmetry. There's also this non-onsitable symmetry. And then there's also this onsitable but not onsite symmetry. So this is very similar to the operator that I wrote before. I just kind of simplified it. So this is a control Z gate. It acts on 2 qubits. And as I mentioned before, this is non-anomalous. This is anomalous in 1+1D. And this one, it looks like it might be anomalous because it's not on site. But you can show that if you tensor in with appropriate ancillas, with an on-site representation of the symmetry, and you do a locality-preserving unitary transformation, then you can actually make this guy onsitable. So this is actually also anomaly-free, just to give you some intuition. So this, you could, with appropriate ancillas, you can find a trivially gapped symmetric Hamiltonian. And so in this context of what I mentioned earlier of these lattice models in 2+1D, and all of these unitary finite internal symmetries, there are examples of symmetries that are not onsitable and not gaugeable, so you can't couple them to dynamical gauge fields. And they emit trivially symmetric states. In fact, they emit symmetric product states. And there's some also similar work that's in progress with Tu Lang and Dominic Els that also kind of discusses this topic. So the main results that we have include an index for 2+1D internal unitary finite symmetries. Given this cohomology class omega, and this takes coefficients. So this is G, your group, and this coefficient is in Q, the rational numbers under multiplication. So what this omega is, it's a function from G cross G, so it takes in 2 group elements and gives you a rational number. And we'll see that this rational number is actually related to quantum cellular automata, QCA, in 1+1D. So there are different kinds of 2+1D internal unitary finite symmetries, and they can be labeled by this index, this 2 cocycle that takes in 2 group elements and gives you a rational number. We can prove that this 2 cocycle has to be trivial for an onsitable or gaugeable symmetry. Furthermore, for every 2 cocycle, we have a fixed point construction of the symmetry operator, so the unitary operator that acts on the Hilbert space. And we can show that this unitary operator has a symmetric product state, has a symmetric commuting parent Hamiltonian. So it's really kind of seems non-anomalous in that sense. And there's also a corresponding 3+1D G-protected quantum cellular automaton. I probably won't get much to this, but there's a close relation between, I'll mention at the end the relation between this QCA and this non-onsitable symmetry. Okay, so the main result is that, so I should mention that in 2+1D, there's also an H4 G with coefficients in U1, invariant for symmetries that are anomalous in the usual sense. So there's an obstruction to both trivially gapped state and to gauging. So in addition to this index, we have the second index that distinguishes also symmetries that admit trivially symmetric product states and yet are not gaugeable. As a side result, we'll also have a construction for an entangler for an elusive symmetry-protected topological phase. What do I mean by entangler? Well, as I mentioned before, SPT is a short-range entangled state. It looks kind of boring in the bulk. So what that means is that if you have an SPT, then you can prepare it from a product state with a circuit. Usually, you can prepare it from a product state with a circuit. The only problem is that the circuit has to contain gates that break the symmetry because the state is not adiabatically connected to the product state if you maintain the symmetry, but it is if you break the symmetry. But then one might have a question, if I want to prepare a given SPT, what is the circuit that I need to act with? So how do I get the circuit to prepare the SPT that I want? As I mentioned, we'll mention later in this talk, there are broad classes of SPTs where we know how to do this preparation. we know how to construct the circuit. But there are certain SPTs where we didn't know how to do that. And it turns out that the non-anomalous but not gateable symmetries that I'll mention in this talk can serve as an SPT entangler for some of these SPTs that have previously have not had entanglers that we knew of. Okay, so I will shortly get into a very simple example, but I should mention first that these kinds of non-onsitable symmetries have appeared in the literature. So back in 2017, there was a paper by Adrian Poe and collaborators that discussed something called the radical flow case circuit. So this is an interesting flow case circuit. So what a flow case circuit is it's a time periodic system. And so you can imagine driving a system with a time periodic drive. And so that means that you have a flow K unitary that describes the evolution over one period. And so they were studying this kind of circuit from the context of flow K dynamics. But what you also find is that if you can take their flow K unitary that describes the time evolution over one period, and you take it to the fourth power on any closed manifold, then it's equal to 1. So this is locality preserving. Its fourth power is equal to 1, so you could take it as a Z4 symmetry of the system. And what you can also show is that if you have a toric code ground state in this lattice system, then this UG implements EM permutation. So every period, the electric and magnetic anions get exchanged in the toric code ground state. So it was also interesting to study from that perspective. A very crucial property of the system, of the symmetry that we will be using is that if you take this UG and you restrict it, so initially you consider it on some closed manifold like a sphere, and then UG to the fourth power is equal to 1. However, if you restrict the symmetry to patch, so you take a region, a large disk A, and then you take it to the fourth power, what they found is that this guy will give you a translation square. So it translates a qubit, 2 qubits basically, if you take it to the fourth power. And what we'll show is that that means that it's not onsitable. So because UGA to the fourth power is equal to translation square, it's not onsitable. However, there are no anomalous Z4 symmetries in 2 plus 1D. So if you look at the classifications of anomaly via H4 class or even cobordism, what you'll find is that there's a trivial classification of anomalies in 2 plus 1D. Another way to think about it is there's no non-trivial Z4 SPTs in 3 plus 1D. And so this can't possibly be related to anomalies in the usual sense where people think about, say, boundaries of SPTs or obstruction to a trivially gap ground state. Why is this UG to the fourth power is equal to translation square indicating non-onsitability? Well, let's consider the case where you just have an on-site symmetry. So in that case, if you restrict to a large region A, then there's a natural way to restrict it, which is you just take these symmetry operators where R is in A. So there's a clean and natural way to restrict an operator in the case where the operator is on-site, so it's a product of on-site operators. However, there's an inherent ambiguity whenever you restrict a unitary operator, you can always decorate the restriction with a locality preserving unitary along the edge. Because a restricted symmetry operator is just something that acts like the symmetry operator in the bulk and acts as the identity very far outside of the bulk. However, you can always decorate the truncation, the restriction, by a locality preserving unitary on the edge that doesn't change the action in the bulk and also doesn't change the action far outside of the bulk. So this U partial A, this operator that represents the ambiguity of how you restrict this symmetry. This is a 1 plus 1D locality preserving unitary, and those have been classified for these qubit type of Hilbert spaces. So this is a unit translation. So as I will mention shortly, you will be able to compute an index that takes value in 2 to the n. So this n is basically the number of qubits that you're translating in the positive direction. So what that means is that if you take UGA to the 4, where this is an on-site symmetry, then that will always come with a fourth power of translation up to some finite depth circuit on the boundary. So this will look like identity in the bulk it will look like identity outside of this region A. And along the boundary, it can be a translation to the fourth power times some finite depth quantum circuit along the boundary. However, as we saw earlier, the radical full case circuit, if you took it to the fourth power, it's equal to translation square. And so it's definitely not an on-site symmetry, because if it was on-site, it would have translation to the fourth power. And if you work a bit harder, what you can convince yourself is that it's actually not equivalent, meaning equivalence under tensoring with ancillas and doing a local unitary transformation is not equivalent to any on-site symmetry. So it cannot be made on-site, even after you tensor in with ancillas. And what that means is that UG can't be gauged and it can't be made on-site. However, it does not describe the boundary representation of Z4 associated with any non-trivial 3 plus 1D Z4 SPTs. So those don't actually exist. Okay. Now, to understand a more general classification of these kinds of non-unsightable but non-less symmetries, we need to review some aspects of QCA, and especially QCA 1 plus 1D, which have been completely understood. So a quantum cellular automaton is a strict locality-preserving unitary, which means it takes local operators to nearby local operators without any tails. So it takes compactly supported operators to nearby compactly supported operators. And we define equivalence up to finite depth quantum circuits. So it's these kind of locality-preserving unitaries modulo finite depth quantum circuits. So we say that two QCA are equivalent if they just differ by a circuit. And by finite depth quantum circuit, what I mean is a circuit that has finite depth. So even as you take the system size to infinity, the action of the circuit can be implemented with a finite number of rows of these kinds of commuting gates. And in 1 plus 1D, this classification of locality-preserving unitaries modulo finite depth quantum circuits was completely classified in a paper by Gross et al. In 2012. And they gave a GMVW index, these are the authors, that takes as input a locality-preserving unitary and pops out a number, a rational number P over Q. And so the idea is that these non-trivial QCA 1 plus 1D all have to do with generalized translations. And the idea is if you have a translation that is a locality-preserving unitary because it just takes operators to nearby local operators. However, a lattice translation can't be generated by a finite depth circuit. One way to think about it is in the continuum, of course, translation can be generated by the momentum operator. However, in lattice systems, you can't you can't do e to the IHT to generate translation when you discretize the space. So in 1 plus 1D, the non-trivial QCA are all generalized translations, and they can be labeled by an index P over Q that tells you how many qubits are translated to the right versus translated to the left, or what's the Hilbert space translated to the left versus translated to the right. So for example, if this P over Q is 2, what that means is you're translating a qubit to the right. If this P over Q is, say, 2 over 3, that means you're translating, you can think of this as having 6-dimensional local Hilbert space formed by a qubit and a Q-chip. So this is a 2-level system and this is a 3-level system. You're translating the qubit to the right and then the Q-chip to the left. So this P over Q just labels some generalized translation of what kind of operators are moving to the right and what kind of operators are moved to the left under this locality preserving unitary. And this is actually something, this P over Q is something you can actually just compute. I won't go into the details, but basically you take some operator algebras associated with some sufficiently large regions, and then you can just compute this P over Q number. Okay, so how do we associate this Tuchel cycle with any representation of a symmetry in 2 plus 1D? So the first thing to do is we have are a representation of a symmetry. So we have a bunch of unitary operators that act on the Hilbert space. And without loss of generality, if it's a locality preserving unitary in 2 plus 1D, we can actually assume that it's and it's finite, then we can actually assume that we can truncate it. So we can restrict it to a region A. And so now what we have are a bunch of restricted symmetry operators that act as the symmetry in the bulk of A and act as identity elsewhere. And now what we can do is we can define this omega A GH, which is a locality preserving operator in 1 plus 1D that's supported along the boundary of A. How we can compute this is we take UGA and UHA and then UGHA inverse. So because this looks like UG in the bulk of A, this looks like H in the bulk of A, and this looks like GH in the bulk of A, this is identity in the bulk of A, and all these operators look like identity far away from A, so this operator is just supported along the boundary of A. And you can show that because each of these operators are locality preserving, and their restriction is locality preserving, this 1 plus 1, this 1D unitary is also locality preserving. So now we can define a 1D locality preserving unitary associated with any two group elements. And then the index is just going to be the GMVW index of this locality preserving unitary. So what this does is it takes as input two group elements, and because this is a rational number, it will spit out a rational number. But it's not any function from two group elements to the rational numbers. It defines a second cohomology class. So what that means is that there's a constraint on this function. So there's a cocycle constraint. And this cocycle constraint just arises from the associativity of the symmetry operators. So if you assume that the symmetry operators UG, A, UHA, UGHA, or UKA, those have kind of an associativity condition, then what you'll find is this two cocycle condition. Furthermore, we can say that two of these omegas are equivalent if they differ by a co-boundary. So cohomology class is cocycle modulo co-boundary. And in this case, this actually arises naturally because it just defines an ambiguity is related to the ambiguity of how you restrict the symmetry. So because you can add any locality preserving unitary when you restrict the operator, that comes naturally as this two co-boundary. So the short story is it's not just any function of two group elements of the rational numbers, it's a particular function satisfying some particular conditions as two cocycle conditions and some equivalence relations as two co-boundary condition. But it's a well-defined kind of mathematical object that you can associate with any representation of a unitary finite symmetry in 2 plus 1D. And we're going to now give an extremely simple example with the group Z2. So what this Z2 symmetry is going to do is it's going to, it's a locality preserving unitary in 2 plus 1D, and it squares to the identity on any closed manifold. However, if you restrict it to this region A and you square it, you'll get a translation along the boundary up to a finite depth quantum circuit. So from the same argument as before, if you just modify the restriction, then it would be an even number of translations up to a finite depth quantum circuit. So because it's an odd number of translations, that actually means that it's not onsiteable, even with this kind of co-boundary ambiguity. Okay, so the simple example is as follows. We consider a 2D lattice, and there are faces and there are vertices. The sigmas act on the faces and the taus act on the vertices. And the symmetry operator, and all these are just cubed, so they're just two-level systems. The symmetry operator acts as follows. It does a spin flip on all of the faces, and then it does a translation on the vertices according to the sigma z domain walls. So this is a functional, this S. It takes as input a domain wall configuration on the faces, and then it does a translation on the vertices accordingly. You can check that this, although it's not completely obvious, this unitary is actually a finite depth quantum circuit. It's sort of a control swap circuit, but you can write it in a finite depth way. So what it does is if there's a domain wall configuration on the sigma z's, then it will do a translation on the taus such that the up domain is to the left and the right down domain is to the right. And the symmetry is locality preserving. So you can check that if you conjugate any of the sigmas and any of the taus, it takes it to kind of nearby operators. So this U just takes sigma z to minus sigma z, and it takes sigma x to an operator supported in the vicinity of this plaquette here. And it also takes tau xyz to operators supported on I, J, K, and L. So in the vicinity of this site I. So this is the actual transformation, but you don't need to worry too much about it. Just know that this is supported, this OP is supported in the vicinity of this plaquette P. And now we can also calculate the index. So to calculate the index, let's consider any domain wall configuration. So this is our initial state psi, and we're going to consider a states where all the spins in the, we're going to consider a restriction of the unitary, so it acts trivially in the spins above this black line here. So the symmetry is restricted to this region A, which is below this black line. And you can see that this particular configuration below the black line has a domain wall here. So when you act with UGA ones, then you flip all the spins. So we flip all the spins, and then we also do a translation such that the up spins are to the left. Now, when we do it again, we flip all the spins again, and then we do a translation so that all the up spins are to the left. And you can see with a bit of work that this does nothing to the bulk of A, so it acts like a Z2 operator. However, it implements a translation up to some finite depth quantum circuit on the boundary of A. So you can do this for any kind of domain wall configuration, and what you find is that as an operator, this U restricted to the region A squares to a translation along the boundary of A up to a finite depth circuit. So this is just a finite depth quantum circuit. So now you can compute these omegas, and what you find is that omega 0, 0 is omega 0, 1 is omega 1, 0 is 1. However, omega 1, 1, so 1 is the non-trivial group element, is equal to 2. 2 labeling the qubit translation along the edge here. And so what you can show is that this is actually a non-trivial cohomology class. So, so this defines an example of a non-onsiteable symmetry with a non-trivial index.
Caroline, I failed to understand the direction of translation that you make from this domain wall thing. Did you specify the direction of the translation that you?
Yeah, so here we define the translation as so that the up
Okay.
domain is to the left. Yeah.
So,
But
okay.
then there's, yeah. I should also mention that what we also could have computed is omega 1, 1 is 1/2. That would have been a translation to the left, actually. However, those two differ by a co-boundary. So those are actually equivalent as cohomology classes. And the reason is because a translation to the right and a translation to the left, that differs by kind of 4, which is a perfect square, which is kind of a double translation. And so the fact that this is non-trivial is not just because this omega 1, 1 is equal to 2. You could have also computed omega 1, 1 is 1/2, but those are equivalent when you consider cohomology class. Does that make sense?
Thank you.
Yeah. Okay. So so I wrote the symmetry operator before. And what you can show is that there's a trivial product state that respects the symmetry. So we just put all the sigmas into the +1 eigenstate of sigma x and all the taus into the +1 eigenstate of tau z. And this respects the symmetry. And the reason is because what this S will do is it will translate the taus, but the taus are in a translation symmetric state anyways. So then it doesn't actually do anything on the tau states. So because the translation acts trivially on the taus, and this clearly just stabilizes this sigma x's, this is actually symmetric under the symmetry, even though it's a product state. So this symmetry is not uncitable. However, there's a trivially symmetric product state. And if you work a bit harder, you can actually come up with a symmetric parent Hamiltonian for this state. So this is a sigma x on each plaquette, and this PP is a projector that's localized near this plaquette. And so this PP, you can think of it as locally projecting into the tau z equals +1 subspace for all of the tau z's, these 6 tau z's in this plaquette. And then this sigma x is actually symmetric in this +1 eigenspace of this projector. So it's the details are kind of long if you actually want to write down the Hamiltonian, but what you can convince yourself is that this is each term commutes with the symmetry, and they also commute with each other, and there's a unique ground state on any closed manifold, which is just this product state. So it seems the symmetry seems extremely trivial from this perspective. It doesn't actually give you any constraints for the low energy physics when you're on any closed manifold. And so what you can show with a bit of work is that for these finite internal symmetries, unitary symmetries, coupling to dynamical gauge fields is equivalent, being able to couple to dynamical gauge fields is equivalent to being able to make the symmetry on-site. However, you might also ask, so those kinds of non-on-siteable symmetries that I showed earlier are not on-siteable and also not gaugeable, dynamically gaugeable. However, you might also ask, what about coupling to background gauge fields? And usually, even for anomalous symmetries captured by this H4 class, you can still couple them to background gauge fields. So for symmetries that people are used to working with, even if they're anomalous in the usual sense, you can couple them to background gauge fields. However, we'll show that for this kind of symmetry, it's rather unusual in the sense that you can't even really couple it to background gauge fields. So what does it mean to couple to background gauge fields? Well, it means, coupling to a flat background gauge field means that there's an assignment of group elements to each of the links. So you can think of this as the state of the gauge field, and it's completely fixed by the matter degrees of freedom. So this Gi is a group element on the vertices on the so-called matter, and then this Gij is associated to the links, and this Gij is simply given by Gi Gj inverse. So coupling to background gauge fields allows you to do kind of local symmetry transformation, and allows you to get kind of to do local symmetry transformations and insert defects. So in order to do that, we say that a symmetry action is background gaugeable if there exists locality-preserving unitaries, these curly U's. And these curly U's are a function of each of the group elements on each of the vertices. And this lambda is just our lattice, such that if Gi is equal to G for all of the sites, then this locality-preserving unitary is just your symmetry, your global symmetry action. And if Gi is equal to, Gi prime is equal to Gi times H for all I, then this is proportional to this curly U Gi times a global unitary that's associated with the symmetry element H. So this is just matching with the global symmetry action. And what we also say is if this Gi prime is equal to Gi for all I in some region R of your full lattice, then these two locality-preserving unitaries only differ by some locality-preserving unitary supported within a finite distance of R. So if these different symmetry configurations differ only in some region R, then you can get these locality-preserving unitaries by some unitary supported within some finite distance of R. So intuitively, what you're doing using these UGIs, this W is you're kind of moving and fusing defects with local unitaries. Why does this allow you to couple the background gauge fields? Well, it allows you to define a symmetric, for any symmetric Hamiltonian, you can define a symmetric gauged Hamiltonian, which is associated with a different kind of configuration of these GIs by just conjugating your original Hamiltonian. So if you see that if all the group elements are just one, then are just G, then this doesn't change your Hamiltonian at all because your Hamiltonian we assume is symmetric. However, for example, if you only have I is equal to G for some patch and identity elsewhere, then this will do a symmetry transformation only on that patch. And so you can think of this as doing a gauge transformation on the original Hamiltonian. So for example, if we have our lattice ABC and we can assign group elements G to region A, H to region B, and K to region C, then we will choose B to be large and finite for the following argument. And what you can show is, and I should mention that this proportionality means up to a phase. So dynamically, and the reason why is because all we really care about is this Heisenberg evolution. So these phases don't really matter if you're just doing Heisenberg evolution. So because the phases cancel between this U and U inverse. So what you can show is that UG 1, 1. So the group elements are G here and identity, and UH1, and GH is proportional to UGH1. So you can just derive that using the 3 assumptions that I mentioned earlier, but it's also kind of intuitive. Furthermore, what you can show is that this UHH1 is this UHA, which is this group element A in this region A, up to a finite depth quantum circuit. And the reason is we can use this local movement operators to move this defect using on these local blocks here, and then act on these local blocks here. So once we act with that depth 2 circuit, we've moved this defect from the boundary of A to the boundary of B. We can similarly do that operation on UGH1. So W1 and W2 are just finite depth quantum circuits. However, then this guy is also, you can show that this UGA, UHA, UGHA inverse is also a finite depth quantum circuit, but in order for it to be a non-trivial QCA, which implies that this omega is a non-trivial QCA, and in order for the index little omega to be non-trivial, this big omega has to be a QCA. So if this is a finite depth quantum circuit, then that means that the little omega has to be a trivial second cohomology class. And so what this says is that if we could background gauge this symmetry, then the second cohomology class has to be trivial. So because we already evaluated the second cohomology class for our particular D2 symmetry and we found that it's non-trivial, then that means that we can't even background gauge the symmetry. We can't even couple it to background gauge fields. And we can't define like defect Hamiltonians, and we can't move those defects using local unitaries in a consistent way. And some of you might be familiar with defect Hamiltonians in the context of, for example, if you have periodic periodic boundary conditions, you can also insert a defect that corresponds to the flux through that periodic boundary condition, flux to the torus. And in that case, for example, you can act with, you can flip the ZZ coupling of an Ising system on a single site. So that's kind of insertion of a defect. And what you can show is that those defects can't be moved in a consistent way that corresponds to coupling to background gauge fields. Okay, so as a side application,
Sorry,
yes,
can I ask a question?
yes.
So it seems to me that in the previous construction, you were like moving defects and seeing the fact that when they fuse, they implement projectively the symmetry. So, or if it's not, how is this construction different from the usual fact that when you have projective implementation of a symmetry, you cannot gauge it?
So an anomaly is, so there are anomalies in 0 dimensions, which are associated with just the fact that the symmetries are represented in a projective representation. In the example that I gave, there wasn't actually any relation to projective representation. The symmetries fuse to a translation along the junction. And so there wasn't actually any projective representation of any symmetry from that context. Did I
Because
misunderstand your
I mean,
question?
no, you understand my question. Probably I don't understand what you were saying. So, like in the previous slide, there were these defects, and you move together and you say, okay, but when I fuse them, I always have the ambiguity of having a phase in principle because I'm just looking at adjoint actions, right?
Okay.
Yeah,
So you're talking about here the coupling to background gauge fields.
yes.
Yes. So one way to say is if you have this phase here, that's usually okay for background gauging. That's not okay for dynamical gauging. And so we're allowing for that phase, but we're saying that we can't even do this procedure even if we allow for the phase. And so we can't even background gauge the system. So we can't have any phase here, but even if we allow a phase here, that doesn't, we can't get a consistent definition of these curly U operators.
So, like for you, if I understood, the background doesn't mean that you project onto the singulet of the symmetry. This
Sorry,
is
can
the
you say that again?
dynamical. So, like for you, dynamical is when you project the Hilbert space into the singulet of the symmetry.
So okay, by dynamical I mean that what we can also do, so this is just background gauge field. So you can think of it as just like some parameter in your system. But what we can also do is we can introduce a Hilbert space of actual gauge field degrees of freedom, and then add dynamics to that Hilbert space. So that's what I mean by dynamical gauging, is that you actually add a Hilbert space for those gauge fields and the actual dynamical degrees of freedom. So there is kind of a relation between whether this is equal or whether this is proportional to, in relation to whether you can upgrade this background gauging to dynamical gauging, which is when you don't treat the gauge field as a parameter, but actually as a dynamical degree of freedom. But here we're saying that even if you don't do that upgrade, even if you just try to do background gauging, that this procedure doesn't work.
Okay, thank you.
Okay. Yeah, so usually dynamical gauging is a way that people kind of use to define anomaly, and that's kind of also what I referred to previously in this talk when I was discussing like the different ways that people define anomaly. Dynamical gauging is rather similar to making a symmetry onsiteable, and you can make that similarity precise in the context of finite unitary symmetries.
Okay, thank you.
Another way to think about it is dynamical gauging is if you can write down a set of Gauss laws that they actually form. For Z2 symmetry, the Gauss laws actually commute with each other. For background gauging, all you need is those Gauss laws to commute up to a phase. Here, even if they commute up to a phase, we can't kind of define them consistently. So it's kind of a stronger obstruction in that sense. Okay. One application of these symmetry operators that we can construct are they give entanglers for SPTs. So what is an entangler? As I mentioned earlier, it's a unitary circuit that takes you from, say, a product state to a non-trivial SPT state. And one question that you might have is, given a desired SPT state, how do you construct this unitary? How do you construct this circuit? And these circuits have been constructed for broad classes of SPTs. So there is a broad class of bosonic SPTs called incohomology SPTs. And those are classified by kind of H D plus 1 of G with coefficients in U1. And so for any of, this is the spatial dimension. So for example, in 2 plus 1D, it would be H upper 3 of G with coefficients in U1. So for any of these kind of bosonic incohomology SPTs, we know how to entangle them. We know how to go from a product state to these kind of non-trivial SPT states using a circuit. And for a broad class of fermionic and supercohomology SPTs, we have an explicit construction for this entangler as well, at least in low enough dimension. And these entanglers are rather nice. So these USPTs that entangle these SPTs, they're finite depth quantum circuits, and they're also symmetric as a whole. So they contain gates that break the symmetry, but if you take all the gates and you multiply together, the USPT is actually symmetric as a whole. So it not only takes a symmetric state to another symmetric, a symmetric product state to a symmetric SPT state, but the operator itself is symmetric as a whole. It just contains symmetry breaking gates. So there's a kind of systematic construction for broad classes of SPTs. How do we entangle them, say, from a product state? However, there are also SPTs that don't fall into those classes. So one example is in 2 plus 1D, there's a fermionic SPT with symmetry group Z2 cross Z2F. This is fermion parity. And there's a Z8 classification labeled by this nu from 0 to 7. The Z8 classification is closely related to the Z8 classification of fermionic systems with time reversal symmetry in 1 plus 1D. So when nu is even, the SPT falls into this supercohomology classification, and we know how to construct a symmetric entangler. However, when nu is odd, it doesn't fall into this supercohomology classification, and we don't know how to entangle this SPT actually. And provably, you can show that there's no symmetric entangler. So the best you can do is a unitary operator that takes you from a symmetric state to a symmetric state, but the operator itself is not symmetric. And so in Tarantino and Fitkowski in 2016, they constructed a commuting projector parent Hamiltonian for this root Z2 cross Z2F SPT phase. But even though they constructed the commuting parent Hamiltonian, they understood the ground state, they didn't have a way to entangle the ground state from a trivial state. And so there's a fermionic version that is rather similar to the bosonic Z2 symmetry that I showed earlier. And instead of bosonic spins on the vertices, you'll instead put Majorana fermions on these edges. And it's rather similar. So it performs a translation on the Majoranas conditioned on the domain wall state of the faces. And in this context, there's a Z2 symmetry generated by, again, all the spin flips on the faces, but now these other degrees of freedom that you're translating are actually fermionic. Now, it's not quite so simple. It's actually a Z4 operator, and you need to consider some plus minus signs associated to something called the Castellan orientation to maintain fermion parity, but the intuition is that it's actually quite similar to the Z2 symmetry, bosonic Z2 symmetry that I mentioned earlier. And what you can show is that this is a finite depth quantum circuit, a unitary operator that maps a trivial product state to this Z2 cross Z2F root SPT state. And so it's a SPT entangler in the sense that it takes you to the SPT state, although the unitary itself is not fully symmetric. So there are some comments in order. So one is that this second cohomology class is not invariant under RG flow. So anomalies in the high energy context are famously useful because they are invariant under RG flow. And so what that means is that the anomaly structure is you can compute it in the UV, but then it also is implemented in the IR. Now, this index that we found here is not actually invariant under RG flow, which I can mention more about. And this is related to the fact that certain operators on the lattice in the IR, they can actually trivialize. So you really have to be careful about this UV to IR mapping, especially with respect to lattice models and continuum field theories. We also have a construction. So I gave you a particular example where G is equal to Z2. But we also have a construction for general second cohomology class, general two cocycle, given any input G. And then we also have a construction of a 3 plus 1D QCA. So this is, as I mentioned, a QCA is a locality preserving unitary modulo finite depth quantum circuit. But you can also ask what's the classification of G-symmetric locality preserving unitaries modulo G-symmetric finite depth quantum circuit. So G-symmetric circuit meaning a circuit built out of G-symmetric gates. And there's a close relationship between G protected or G-symmetric QCA and these non-onsiteable symmetries in one lower dimension. And in fact, you can also go even higher dimension to, there's a related G-symmetric flow K phase in 4 plus 1D. But all those things I can say more words about, but we also have constructions of these guys that haven't been really found in the literature before. And then there are also other classes of examples that you can construct in bosonic and fermionic settings. So at least in 2 plus 1D, we believe that now there's two indices, this H4 class and RH2 class. But then in higher dimensions, you can play around with, there may be a richer classification that we haven't explored in full. And even though it doesn't have consequences for ground state properties, there may be consequences for higher energy spectrum of any symmetric Hamiltonian, which we haven't explored so much in this work, but I believe in Dominic's paper that will be explored a bit more in depth. Okay, so that's all I have for you today. Thank you for your attention. Yeah, if there are any questions, I can take them now.
Thank you very much for this beautiful talk. Are there questions or remarks?
So can I ask a question?
Yes, go ahead.
Yeah. So yeah, thank you for very interesting talk. So at some point you mentioned that if you restrict the action of the symmetry operator to some region at the boundary, you find square root of translation. Then in that case, it's not onsiteable, if I remember correctly.
So we never actually got square root of translation here. So here indeed UGA to the 4th power is translation square.
Yeah.
So you might say like, oh, maybe I should associate with UG a square root of translation. However, UG actually acts rather non-trivially all in the bulk. So you can't really identify it with a 1 plus 1D index like a square root of translation.
Yeah. So yeah, okay. So my question is that instead of this UGA, if you consider square of this guy, then okay. Oh, maybe that makes sense. So if
Or in this case, right, for the Z2, you might also
okay,
associate this with square root of translation, but the UG acts non-trivially in the entire bulk. Yeah.
So if the group is Z2, then this is always the case, or it depends on the more details how Z2 is implemented.
What do you mean this is always the case?
So in your previous example, the group was Z4, then in that case, you find non-onsitable transformation. But if I take square of the previous Z4, then it becomes Z2. Then in this case, this is onsitable. Right? So is this dictated completely by the group?
It's dictated by this second cohomology class, right? So
Oh, okay, okay. I see.
right. Yeah, so here what we have is UG. So
Okay.
G is GG, and then the G square is just the identity operator. So there's a trivial way to restrict it. So then the useful kind of thing to compute is omega GG, which is going to give you a translation, a single translation. Otherwise, you might worry that you can get rid of these kind of translation by appropriate redefinition of the truncation, or equivalently by shift by co-boundary. But in this case, it's
Okay.
truly, yeah.
Yeah, thank you. Thank you.
Mhm.
Can I ask a simpler question?
Yeah.
So you showed us an example or examples in which you have non-onsitable symmetry, which have non-trivial index, but still the symmetry is trivial in some sense that you can find simple state. But is it correct to understand that these are exceptions, and usually if you have non-onsitable symmetry, then they are non-trivial? And
It depends on what you mean by usually.
yeah, or do you have a bunch of examples of that kind?
So there are other examples you can construct, but I would say that maybe you're right in that usually that's the case, because in all of the examples of at least the finite unitary symmetries that people have studied in the literature, and in the context of anomalies, that has always been the case,
Okay.
which is why people kind of believe that those two definitions are the
Okay,
same.
okay. Oh yeah, all right. So that was the history, and then you cooked up these new examples in which the symmetry is non-uncitable, but still is trivial in this sense. But so, how did you find this? Did you find this by accident, or is there any philosophy leading you to these examples?
Yeah, so I think it came up because um, there is this belief that, and you can also make it more concrete. The gauging is equal to making uncitable and all those things. And but there was this work back in 2017 of this unitary, and people back then didn't view it as a symmetry, but it's a locality for observing Z2 unitary. And so, but this had this funny behavior that it didn't seem like there was a way to get this boundary translation if you had an on-site symmetry or an on-siteable symmetry. So that was the starting point, because yeah, there was this example that it seemed to violate the expectation. And then the question was, okay, this example, we believe that it's not anomalous, because if you look at the anomaly classification of Z4 in 2 plus 1D, it's trivial. The problem with this example was that it was difficult for us to construct an explicit short-range entangled state that was symmetric under this symmetry. You can construct toric code, which is invariant under this symmetry, but toric code is non-trivial, right? It's topologically ordered. And so, so then we had an idea of how you might go about constructing a trivially symmetric state if you tensor in ancillas, but it was rather complicated. So then we had to cook up another construction that had the same, like, that also had a non-trivial index, but it was very obvious in the Z2 example that I gave that you can actually construct a trivially symmetric product state. It's not so obvious from this one. All you can see is that it's not uncitable, and yet there are no Z4 anomalies in 2 plus 1D.
Okay, thank you.
Any other questions? So maybe let me ask, I'm wondering which class of models you are actually studying. Maybe I missed it. Is it are there many? Are there few? When you say gauging, then I start thinking about lattice QCD, but this is probably not what you are doing.
Oh, yeah. So lattice QCD is actually gauge theory, right? So that,
Yeah.
for example, could be something that you would get. So here we're starting with a global symmetry, and then when you have a global symmetry, you can make the symmetry local by gauging it, and then you could result in some kind of gauge
But when you
theory.
say you added dynamical gauge field, should I think about adding like Kogut-Susskind Hamiltonian to the system, or what makes it dynamical?
So in this case, we actually can't gauge the theory, but you can think of by adding dynamical gauge field, what that means is that you have your global symmetry, and then you add in new degrees of freedom, your gauge fields. And
Okay.
they're constrained by Gauss law. But your
Okay.
gauge fields actually have a Hilbert space and can fluctuate.
Okay.
So that's what I mean by like dynamical gauging. And in this case, people often associate kind of anomaly with an obstruction to dynamical gauging. Because intuitively, if you're able to kind of those local degrees of those allowing the fluctuations of the gauge field would allow you to do kind of local symmetry transformations that would be inconsistent with each other because of these extra phases that you have when you have anomaly of the usual sense. And in this case, what we're showing is that in addition to obstruction to dynamical gauging, this kind of symmetry also has an obstruction to even coupling to background gauge fields and things like that. Does that answer your question?
Yeah, I think to a large extent. I have another question. So I understand you define your systems by giving local Hamiltonians, right?
So the
Or
system is actually just defined by the symmetry. So the idea is that what you can consider is a Hilbert space, a tensor product Hilbert space.
okay.
And on that Hilbert space, you have some symmetry operators, and then you can consider any Hamiltonian that commutes with the symmetry
Okay.
and ask if there's a trivially gap symmetric Hamiltonian.
Trivially gap symmetric means that there is a gap? Or?
Yeah, so in particular, we think about gapped theories, meaning that there's a gap in the energy spectrum above the ground state that remains order one in the thermodynamic limit. And when in certain kinds of representations of the symmetry on the Hilbert space prevent you from finding such a gapped Hamiltonian that commutes with the symmetry. And that's another kind of, that's what we take as to be the anomaly here.
Okay. Yeah, I'm asking also because one thing I learned about lattice systems is that it's pretty difficult to prove that it has such a gap uniformly in the size of a lattice. So what's your take on this? You just say your theory holds abstractly for all Hamiltonians which have a gap, or do you have some implicit assumptions behind, or not? What about the
Right.
existence of Hamiltonians which satisfy all your assumptions? I mean,
Yeah,
maybe it's
so
a similar
here
question as House.
Here it wasn't too difficult because we actually have a commuting Hamiltonian. So we have this commuting parent Hamiltonian. And so uh, here. So because this is commuting, there's just a gap of size one, basically, no matter how large you make the system. Because you can take a uniform limit to infinity, just translation invariant, it's commuting, so there will always be a gap. But So in this case, we can pretty much guarantee that there exists a gap parent Hamiltonian in this thermodynamic limit that respects the symmetry. And the other cases, what you can show is that if there's an anomaly in the usual sense, that because of certain ways that the symmetry defects fuse together, that prevents you from realizing a gapped parent Hamiltonian. Um, but in the case that that anomaly vanishes, there's usually systematic methods for constructing examples of such gapped Hamiltonians.
I see. Okay,
So for
and
example,
other
here
question?
as well, like you can tell that this Hamiltonian is just sum over sigma x. They're all commuting, so it's very clearly going to be gapped in the thermodynamic limit.
Oh, okay. So any other questions or remarks? If not, then maybe let's thank the speaker again. Switch off the recording.